CLion, a cross-platform IDE for C and C++. Download now.
Everyone, I'm going to be talking about single producer, single consumer part queue today, how to build an efficient queue. Let's get straight at it. I'm Sarthak. I'm a C++ software engineer working in Chicago. You can find me on my blog or on LinkedIn. So what's the setup of this queue that I want to build? So one, we have exactly one producer and one consumer. Two, it has to be fixed capacity. And as soon as I read fixed capacity, one of the optimization is to pre-allocate the memory when the queue is constructed, as opposed to allocating memory on every push and deallocating it on every pop. And three, and most importantly, the producer and consumers are pinned on separate physical cores and are continuously polling for data. So a use case of this, especially in an industry like mine, like the trading industry, would be that you may have a market data handler which is listening to the exchange messages and passing packets and building order books. And there's another thread, dedicated thread, that is the trading application, which is expecting a new order book and sending and doing some calculations and sending orders based on that. Because this is a fixed capacity queue, we can do a circular buffer implementation. There's going to be the head, which is going to be the read end, and the tail, which is going to be the write end. A basic implementation of this would be using good old mutexes, but it has some shortcomings. Primarily, locking a mutex's blocking call, and the mutex is going to do some expensive system calls. We can do something much better than this. We can use atomic operations to ensure synchronized access to the shared memory of the queue, and atomicity of accessing the head and tail variables. So you can see on the left, I have this push function, which takes in an item. I read the tail and the head, which is the tail load and the head load. I ensure that the queue there's some space left in the queue. And then I add the element to the queue using placement new into my buffer and store the new tail value, which is tail +1. You can see like there's two loads and one store, and these are the atomic operations. So with this, the queue is non-blocking, it's lock-free, but it's still doing strict memory ordering. And we can optimize this even much further. So what exactly is memory ordering? Modern CPUs are allowed to reorder instructions to achieve a higher instruction per cycle count for more efficiency. And this is known as out-of-order execution. So the two lines that I pointed out in the push function, for example, that is creating the element, like constructing the element using placement new and then updating the tail. A CPU can decide to reorder these instructions. And these, in this specific case, this can be catastrophic. So if I update the tail, then the consumer might, before I've actually written the element, then the consumer might consume an element that does not even exist yet. This picture depicts that. So on the top, if the instructions are actually executed by the CPU in the sequence they are in my program, but in the bottom, if I switch the two instructions, that is, I update the tail before I've actually written it to the buffer, the consumer thread reads and destroys the buffer element, which I've not even written to yet. So with atomics, we need to ensure atomicity, but also ensure synchronization of the memory access. And that is where memory ordering comes in. Memory ordering defines how access to memory, maybe non-atomic memory even. For example, in our case, the buffer is like non-atomic. So how the access to this memory is defined around atomic operations. One of the memory orderings is relaxed, which only ensures atomicity and has no ordering constraints. For example, in the case, I know that the producer only the producer thread is writing to the tail, and only the consumer thread is writing to the head. So when the consumer thread reads the head at the very beginning, we can use relaxed ordering. And using these orderings to our benefit, we can optimize the queue further. For example, in the push method now, I'm reading the tail with relaxed memory ordering, and then head with release acquire. So I'll go more. I'll go into details about that. So I profile the queue with inserting 1 million integers and a queue of size 1,000. You can see that originally with the standard atomic, it has 146 milliseconds for operations. With the memory ordering, it's approximately 4 times faster. So just adding the memory, relaxing the memory ordering, it's 4 times faster. Boost queue is still almost 5 times faster, but even doing some further optimizations, the queue becomes a bit faster than Boost SPSC queue. I think I'm out of time, but if you're curious to learn more about this, hop over to my poster boot tomorrow, where I'll talk about further optimizations to the queue. Thank you so much.